Hello, good day. My name is Brian, and this is my reflection on the short course Advanced Polymer Applications in Renewable Energy Technologies. So, to start with the first question on the core concept, the key role of polymers in renewable energy technologies is truly as an enabler. They function as critical components like electrolytes and separators in devices such as fuel cells and batteries. Their properties make them uniquely suitable for these roles compared to traditional materials like metals and ceramics. Unlike metals, which are heavy and consume a lot of energy during production, polymers are lightweight, easy to process, and require less energy to manufacture. And compared to ceramics, polymers offer much greater flexibility and elasticity. A key advantage is their highly tunable structure. We can engineer polymers to have specific properties like ion conductivity, which is essential for electrolytes function in a fuel cell, allowing ions to pass through while preventing the fuel and oxygen from mixing. This combination of being lightweight, flexible, and having highly customizable properties is something metals and ceramics just can't offer for these specific energy applications. Moving on to the most impactful application, I was particularly struck by the use of polymers in polymer electrolyte membrane fuel cells, or PEMFCs. I find this application the most promising, especially in the context of Indonesia. PEMFCs operate at relatively low temperatures, under 120 degrees Celsius, which allows for quicker startup times. This makes them incredibly versatile and well suited for transportation applications like fuel cell electric vehicles, which could significantly address urban air pollution in Indonesian cities. The electrolyte is a solid polymer membrane, which is safer and more robust than liquid electrolytes. Given Indonesia's goals to enhance its renewable energy portfolio and tackle transportation emissions, promoting PEMFC technology for vehicles and even for backup power in critical infrastructure seems like a very impactful and relevant path forward. Of course, there are significant material challenges for both fuel cells and batteries. A major hurdle for polymer electrolytes and separators is achieving high ionic conductivity while maintaining mechanical and thermal stability. For instance, in PEM fuel cells, the membrane needs to be sufficiently hydrated to conduct protons effectively, but operating at high temperatures, which improves efficiency and reduces catalyst poisoning, can dehydrate the membrane. Innovations in polymer structure are key to solving this. As the lecture showed, researchers are developing advanced polymer architectures like sulfonated polyamides and polyallyl ether sulfones. These materials have more rigid backbones for better thermal and mechanical strength. Another approach is creating block copolymers, which allows for distinct hydrophilic and hydrophobic domains. This creates well-defined nanochannels for efficient ion transport, almost like a river within the membranes, even with lower water content. These structural designs are crucial for developing the next generation of durable and high-performance membranes. Finally, after this course, I see the future of polymer research in renewable energy as being incredibly dynamic and central to progress. It's clear that breakthroughs in energy storage and conversion will heavily depend on materials science, particularly on designing smarter polymers. The topic I'd like to explore further is the development of non-precious metal catalysts and how they integrate with new polymer membranes in the membrane electrode assembly. The lecture touched upon the high cost of platinum catalysts as a major barrier. Understanding the synergy between innovative, cost-effective catalysts and the polymer ionomer that binds them is fascinating. Optimizing this triple phase boundary, where the gas, catalyst, and electrolyte meet, seems to be the heart of the challenge and where the most significant performance gains can be realized. I believe this specific area holds immense potential for making technologies like fuel cells economically viable on a global scale. Thank you.